तो हम ये है नहीं, मिस ये बोल नहीं रहे स्टूडेंट से, मैं बोलूँ। अच्छा भाई, जो हम थे A2 फिजिक्स, we're doing oscillations. अच्छा, जो हमारी डिस्कशन हो गई थी, लेट मी एक्सप्लेन यू नाउ द graphical representation of the variation in displacement, velocity and acceleration with respect to time. ठीक है ना? तो ये आपके पास ग्राफ्स जो है ना वो शो हो रहे हैं स्क्रीन पे ना। अच्छा, let me tell you कि if you have this sort of graphical representation for displacement, so this actually represents cosine. This curve is of cosine form. All right, this is a cosine curve. The variation है that takes the shape of a cosine curve in displacement, जो अभी शो हो रही है आपकी स्क्रीन पे। तो इसकी जो आपकी रिलेटेड इक्वेशन है, या जो इसकी इस ग्राफ की जो मैथमेटिकल इक्वेशन है, जो कि वो दैट इज गोइंग टू बी x इक्वल्स टू माइनस x नॉट cos ओमेगा t. ऑलराइट, अच्छा, ये बेसिकली cos is used when you have when the object is displaced from the point of maximum displacement. Yeah, जो variation आपकी आती है displacement है, if it takes the shape of a cosine curve, it does so when you displace the oscillating particle from its maximum position, from the point of maximum displacement. So then the variation in the displacement takes the form of a cosine curve. ठीक है ना? अब basically if you displace it from the point of maximum point of positive maximum displacement, then it would have been plus cos omega t plus x naught. और अगर आप इसको point of negative maximum displacement से displace करते हैं, then the variation is going to be in terms of then the mathematical equation will be minus x naught cos omega t. ठीक होगी बात? ये तो होगी। और इससे फिर आपकी now what can you see, what can you now how can you tell that what is going to be the mathematical equation representing this variation in the velocity? Now this is a sine curve. The sine curve always starts from the mean position, from zero. All right, and we know that at point of maximum displacement you have zero velocity. At point of zero displacement, that is at mean position, you have the maximum velocity. Then again at the point of maximum displacement on the other end, gonna have again zero velocity. ठीक है ना? तो आप बात समझ आ गए आपको नहीं? And so on. So you have now the variation. Now you have in the velocity takes the shape of a sine curve, and so you can write down the equation for v as, now this is a positive, this is a sine curve, and it is like positive in the it's going positive, so it's going to be omega x naught sine omega t. If it would have been going to, अगर ये start होता zero से और जोहा अगर ये जाती negative, would have been with the time, अगर ये start तो zero से होती है, लेकिन अगर ये negative में move करती initially, like this, जोहा, then your mathematical equation for that sort of variation would have been minus omega x naught sin omega t. ठीक है? तो ये बात समझ आ गई बेटा आपको?
जी सर।
बस ये फर्क है। और इसी तरह एक्सेलरेशन के अंदर आप देख लें कि ये आपका that takes a form of a cosine curve, but that is positive. एक्सेलरेशन क्या है? cosine है, but that is positive. Starts from the point of maximum displacement. It starts from the positive maximum value, the acceleration, and we know कि आपके पास जो acceleration है, because initially at time t equals to 0, initially your displacement was minus x, so your acceleration is going to be plus a. ठीक है, it's always in opposite in direction. तो अगर आपकी initially displacement minus x है, तो ये जो आपकी acceleration है, that's going to be maximum and but positive. तो आपको जो shape है ना, that's again it's going to be, that was the variation, the displacement was took the shape of a negative cosine curve. Now the variation, the acceleration is going to take the shape of a positive cosine curve, and so the mathematical equation is going to be omega square x naught cos omega t. Just by looking at the graph, आप जो है ना, you can deduce के इसकी जो mathematical equation है वो क्या होगी, defining the representing the variation. ठीक है, तो यहाँ तक बात समझ आ गई, ओमेगा स्क्वायर एक्स नॉट cos ओमेगा t. अच्छा
जी सर.
now this is your time period. This is your time period as I have marked it. So over here you have one oscillation being completed, and from over here then again, you know, the pattern repeats. You know, if you just look at the graph, so from here after this instant the pattern repeats. So this means that over here you have then the first oscillation got completed. ठीक है ना, starting from here to here you have then your first oscillation got completed. So this time is going to be what we call in physics as time period. ठीक है ना, ये time period. And so this is going to be 2t, क्योंकि यहाँ पे over here you're going to have then the second oscillation going to get completed. So this time is going to be 2 times the time period, 2t. ठीक है, and this is the same. अच्छा, अब आपके पास over here this is the same as time period. ये time period है, time period है. तो आप चाहे displacement या velocity acceleration किसी भी quantity के graph से आप जो है वो reduce कर सकते हैं time periods. And you can just see कि आपके पास जो है ये जो one oscillation है वो कहाँ complete हो रही है. You can always see the graph and find out where you have one oscillation getting completed. That's the point where you after that you going to have pattern repeated. So जिस point के बाद आपका pattern repeat हो रहा है, इसका मतलब ये है कि आपका वो instant जो है उस पे आपकी जो oscillation है वो complete हो रही है, तो that time is going to be the time period. अच्छा, as for the acceleration, मुझे आपको एक चीज बतानी है. This is what we call as deceleration. ये जो हिस्सा है ना, that is acceleration. ठीक है, basically that is acceleration. आपकी जो displacement है meanwhile जब आप ये when you are at A you have positive acceleration maximum, क्योंकि आपकी जो restoring force है that is directed towards the main position and towards the right it is taken as positive. तो आपकी acceleration maximum होगी and it's going to be positive. As soon as you're going to move towards B, जैसे आप B की तरफ move करेंगे तो at B it's going to become 0. ठीक है ना, at B it's going to become 0. अच्छा, एक बात याद रखिएगा, तो अगेन दोबारा बता रहा हूँ कि जो meanwhile when you are moving from A to B आपकी acceleration 0 हो रही है but not your velocity. ठीक है ना, velocity आपकी increase हो रही है. तो remember कि ये from A to B you still have the acceleration. क्योंकि हमने kinematics में AS में पढ़ा था कि जो है आपके पास ये ग्राफ होता है ना, ये वेलोसिटी वर्सेस टाइम ग्राफ, ठीक है ना, और इसमें आपके पास ये जो ग्राफ होता है तो यहाँ पर आपके पास क्या है, ये वेलोसिटी बढ़ रही है बट एक्सेलरेशन क्या हो रही है, डिक्रीज हो रही है। जस्ट बाय लुकिंग एट द ग्रेडियंट रिड्यूस किया, आपकी एक्सेलरेशन डिक्रीज हो रही है। और उसकी मैंने आपको एग्जांपल भी लिख के देता हूँ। जैसे आपके पास है 0, 30, 50, 60, 65, 68 एंड 68 एंड सो ऑन। वेलोसिटी बढ़ रही है लेकिन एक्सेलरेशन डिक्रीज हो रही है। 30, 20, 10, 5, 3, एक चेंज आपका कम होता जा रहा है, एक्सेलरेशन कम हो रही है। तो ओवर हियर आपका सीन यही है कि वेलोसिटी इंक्रीज हो रही है अप टू पोजीशन बी, दैट्स अ मीन पोजीशन, बट एक्सेलरेशन डिक्रीज हो रही है। उसके बाद फिर आपकी वेलोसिटी फ्रॉम बी टू सी, बिकॉज यू आर मूविंग टुवर्ड्स अ पॉइंट ऑफ मैक्सिमम डिस्प्लेसमेंट, सो ऑफ कोर्स यू आर मूविंग अगेंस्ट द रीस्टोरिंग फोर्स। आपकी रीस्टोरिंग फोर्स विल ऑलवेज बी डायरेक्टेड टुवर्ड्स द मीन पोजीशन, और आप फ्रॉम बी टू सी जब मूव कर रहे हैं तो यू आर मूविंग अगेंस्ट द रीस्टोरिंग फोर्स। इट्स जस्ट द सेम एज लाइक मूविंग अगेंस्ट द ग्रेविटी। So when you just throw up the ball, so what happens is आपकी जो velocity decrease होती है, because that resultant force due to gravity going to oppose the motion. So over here, the restoring force is going to oppose the motion as the oscillating particle is going to move from B to C. तो आपकी velocity decrease हो रही है, ठीक है ना? And so आपकी जो acceleration है, first of all, it's going to be negative. Negative क्यों? क्योंकि displacement is towards the right, but the restoring force and the acceleration is going to be towards the left, towards the mean position. तो एक तो वो negative है, and all of this over here you have then आपके पास basically यहाँ negative में acceleration, ये deceleration बढ़ रही है, सही है? ये deceleration है। अच्छा, ये basically deceleration है और negative है। Negative क्यों है? क्योंकि आपकी जो है वो when you are moving from B to C, it's directed towards the mean position towards the left. नेगेटिव तो इस वजह से। और डिसेलरेशन क्यों है? क्योंकि मीनवाइल व्हेन यू आर मूविंग फ्रॉम बी टू सी आपकी वेलोसिटी डिक्रीज हो रही है। फॉर दिस बिटवीन दीज टू पॉइंट्स, ठीक है ना, जो भी आपकी वेलोसिटी में वेरिएशन आ रही है, चेंज आ रहा है, वो डिक्रीज हो रहा है, दैट मींस दैट यू आर डिसेलरेटिंग, एंड दैट डिसेलरेशन इज इंक्रीजिंग विद द टाइम। वो इंक्रीज हो रही है, नेगेटिव डायरेक्शन में इंक्रीज हो रही है। देयर आर थ्री थिंग्स which you have to keep in mind, and that is, one is that the direction is going to be negative because that's directed towards the mean position, towards the left. Secondly, deceleration हो रही क्योंकि B to C में आपकी velocity decrease हो रही, और thirdly ये deceleration भी increase हो रही है, ठीक है ना? आपकी यूनिफॉर्म deceleration नहीं है while moving from B to C, बल्कि deceleration आपकी increase हो रही है, like this, velocity versus time graph, और ये deceleration क्या है? Increasing deceleration, ग्रेडियंट आपका बढ़ रहा है और वेलोसिटी 0 हो रही है। तो इंक्रीजिंग डिसेलरेशन मींस कि आपकी अगर 30 थी, फिर आपकी 20 हो गई, और फिर आपकी 5 हो गई, तो ये डिसेलरेशन इधर 10 और इधर 15, तो ये डिसेलरेशन बढ़ गई, यानी रेट एट विच आपकी जो वेलोसिटी डिक्रीज हो रही है ईच यूनिट ऑफ टाइम में, वो बढ़ रहा है। तो यहाँ पे इंक्रीजिंग डिसेलरेशन है, और ये सी पर आके आपकी you're going to have the maximum deceleration. Now at C, when you're going to move again towards B, तो फिर आपकी एक्सेलरेशन ही होगी, क्योंकि आपकी वेलोसिटी बेसिकली बढ़ी, बट वो एक्सेलरेशन जो है ना वो रिड्यूस होके विल बिकम टू 0 अगेन एट B, और फिर उसके बाद B to A जब भी आप देन अगेन यू गोना मूव, तो अगेन डिसेलरेशन होगी क्योंकि वेलोसिटी फिर डिक्रीज हो रही है, 0 की तरफ मूव कर रही है, वेलोसिटी कम हो रही है, बट दिस टाइम पॉजिटिव डिसेलरेशन बिकॉज दैट इज गोइंग टू बी डायरेक्टेड टुवर्ड्स, क्योंकि डिस्प्लेसमेंट इस डायरेक्शन में हो रही है, तो एक्सेलरेशन विल बी डायरेक्टेड टुवर्ड्स द मीन पोजीशन टुवर्ड्स द राइट, तो डिसेलरेशन आपकी पॉजिटिव है, ठीक है? जो आप बात समझ आ गई, एंड सो ऑन, देन द पैटर्न इज गोइंग टू रिपीट। इज इट क्लियर और नॉट?
जी सर, क्लियर है।
अच्छा, अच्छा, now with the time, how how the energy of the system varies with the time. That's what we need to represent as well. पहले यहाँ जो representation the variation in energy, that was with respect to the displacement. Now how the energy of the system is varying with the time. We know that there are two energy conversions taking place, ठीक है ना, either from kinetic to potential or potential to kinetic. Only these two, ठीक है ना, taking an ideal situation. Now we know that at A आपकी जो at A, that's the point of maximum displacement. So we're going to have the maximum PE, that's blue one, it's representing PE, maximum PE. And then when you're moving to B, you're going to have the B means mean position, so 0 PE. Then to C, on the other hand, at the point of maximum displacement, maximum PE. And then to B, again, you're going to have 0 PE, and then back to A, you're going to have maximum PE. And remember that you're going to have the magnitude for the potential energy positive at all instants. Okay, now, at every instant, the value for both the energies, potential energy and the kinetic energy, is going to be positive, not negative. Okay? That is independent of the direction of motion. And at B, you're going to be the instant when you are at B, that's going to be 1/4 of the time period. When you have moved from A to B, you have that's within a time within 1/4 of the time period. And from B to C, then again 1/4 of the time period, and C to B, then again 1/4 of the time period, and then B to A 1/4 of the time period. So when you are at B, the time is 1/4 of the time period. When you are at C, that is half of the time period. And again, back to B, that's 3/4 of the time period, and back to A, it's going to be T. One value, that's time period. ठीक है, तो यहाँ पे B पे T/4, T/2, 3/4. यहाँ तक बात समझ आ गई आपको? वाह,
जी सर, समझ आ गया.
और kinetic energy, that's the complete reflection of potential energy. Whatever the graphical representation of potential energy is, उसको आप reflect कर दें, ठीक है, in horizontal axis में अगर आप उसको reflect कर दें, that's going to give you the graphical representation of kinetic energy at A point of maximum displacement 0, and then going to maximum, and then coming to 0, then maximum, and coming to 0. ठीक है. अच्छा, for a spring mass system, there's a transformation between kinetic and elastic potential energy. It's not gravitational, that is elastic potential energy. That's elastic potential energy. And the energy stored in the spring. At the top, there's maximum elastic and basically for a horizontal spring mass system. अच्छा, for a on a vertical spring कर देते हैं. There's a अगर vertical spring है तो फिर there's a transformation. There are 3 transformations: kinetic, gravitational, and elastic potential energy. So at the top of the spring, there is maximum elastic and gravitational potential energy. यानी कि ये spring है. तो जब ये आपका extend होके इधर आ जाएगा, ठीक है, ये point of maximum displacement, या फिर ऊपर चला जाए, ये आपकी मेन पोजीशन हो गई. ठीक है, तो यहाँ पर आपके पास क्या कह रहा है, एट द टॉप देयर इज मैक्सिमम इलास्टिक. यहाँ पर मैक्सिमम इलास्टिक है, एंड ग्रेविटेशन, यानी कि मैं इसको ड्रॉ कर देता हूँ। ठीक है, और यहाँ पर मैं तो यहाँ से स्टार्ट करते हैं। एट द टॉप ए बी एंड सी। तो एट द टॉप आपके पास जो ये आपकी मीन पोजीशन है, ये स्प्रिंग है, ठीक है ना, और तो ये आपकी मेन पोजीशन होगी। When you have displaced the spring to A, so at the top you have maximum elastic potential. The spring आपका compressed है, as well as you have the maximum altitude, so you have the maximum gravitational potential. So you have maximum elastic and gravitational, but you have the minimum kinetic. In the middle, there's you don't have any elastic potential. You just have maximum kinetic, and you don't have, but you do have some gravitation. ठीक है? P पे you do have some gravitation, because let's think of this to be as your surface. ये आपका surface ले लें। तो A पे आपके पास maximum gravitational potential, maximum elastic, minimum kinetic. B पे you have the maximum kinetic, you have some gravitational potential, but you don't have any elastic potential because the spring is neither extended or compressed. At C you have again maximum gravitational, minimum elastic, maximum elastic potential, maximum gravitational potential, and again minimum kinetic. ठीक है ना? और between any two instants, the total energy remains the same. If you talk about that is at A and B, total energy is going to get conserved. All right, and अच्छा, basically if you talk about the gravitational potential, तो वो इतनी कम होती है, although यहाँ maximum है, यहाँ सम है और यहाँ दोबारा maximum, लेकिन ये जो इन तीनों पोजीशंस पे जो ग्रेविटेशनल पोटेंशियल की जो वैल्यूज है ना, वैल्यूज हैं, वो बेसिकली इतनी ज्यादा अप्रिशिएबल नहीं होती, क्योंकि आप कोई बहुत ज्यादा एल्टीट्यूड पे स्प्रिंग को कंप्रेस नहीं करते या उसको डिस्प्लेस नहीं करते। तो एट फॉर एन मतलब अगर मैं एक स्प्रिंग मास सिस्टम की बात करूं, स्प्रिंग जिसमें आपका मास वर्टिकली हैंग हो रहा है, तो उसमें जो आपकी जो ग्रेविटेशन पोटेंशियल एनर्जी में वेरिएशन आती है व्हेन दी स्प्रिंग अंडरगोस सिंपल हार्मोनिक मोशन, तो वहाँ वेरिएशन इन ग्रेविटेशन पोटेंशियल एनर्जी कैन बी निग्लेक्टेड, क्योंकि वहाँ आपका स्प्रिंग जो है वो कोई एप्रिशिएबल या सिग्निफिकेंट अमाउंट ऑफ मतलब उसमें उसकी कोई वर्टिकली जो है वो कोई सिग्निफिकेंट डिस्प्लेसमेंट नहीं आ रही, ठीक है ना। एंड even if you pick up any 2 points and you just see the difference between the gravitational potential energy, so again that's again could be neglected, it's very small. So that's why although when you're just talking between you do have potential total energy being conserved at all the points, and at any point the total energy is given by the sum of kinetic, elastic potential plus gravitational potential. But I haven't written it, the gravitational potential energy, because I've just told you that it's not that much significant, so you just can neglect at both of the points between which you are studying. And you have then at end the point, the total energy is going to be given by the sum of kinetic plus elastic potential, and this sum is going to be the same at 2 points. Total energy is going to get conserved. ठीक है ना? ये आपकी elastic potential energy, that's something you already know from your knowledge of AS physics. यहाँ पे दोनों तरफ में प्लस mgh you should add, because you do have some variation in the gravitational potential, but that's very negligible. So you can just skip that. ठीक है ना? Is it clear, Zoha, or not? और यहाँ पे अगर आपको
जी सर।
दो पॉइंट्स में से अगर आपको एक की काइनेटिक पोटेंशियल और दूसरे की इलास्टिक पोटेंशियल पता है तो आप काइनेटिक, that's how you can find out. You can always use that concept of conservation of total energy at any 2 points between the oscillation of between the oscillations in a simple harmonic motion, and then whichever way the total energy is conserved, you can just keep that equal at both of the points and find out any unknown quantity, either mass or velocity or displacement or whatever. ठीक है ना? अब जरूरी नहीं कि आपके पास हर सिचुएशन में जहां आपका ऑब्जेक्ट सिंपल हार्मोनिक मोशन में हो तो उसकी टोटल एनर्जी इज गिवन बाय द सम ऑफ काइनेटिक एंड इलास्टिक पोटेंशियल, डिपेंड्स ऑन व्हाट काइंड ऑफ सिस्टम इज. ठीक है ना? जैसे कि यहाँ पर था, फॉर अ पेंडुलम इट वाज the total energy included was actually the sum of the gravitational potential and kinetic, not the elastic potential. But in case of spring mass system, ठीक है ना, you have then the total energy expressed as the sum of kinetic and elastic potential. So it depends on the situation. ठीक है? Is it clear or not? अच्छा, फिर आपके पास है, now let's talk about resonance and damping. So basically resonance and what's resonance? To know what free and forced vibrations are. Vibrations are a form of oscillations. All right. Or you may think of as a synonym for the oscillation. Vibrations are basically oscillations. ठीक है ना? So to know what free and forced vibrations are and the phase difference between the driver and driven. Now you're going to learn to know what resonance is and how it is reached, and you are going to learn this, going to study this to know what light, heavy, and critical damping are and their effects on resonance. So what is free vibration? Free vibration is where a system is given an initial displacement, okay, and then allowed to vibrate, oscillate. So you can see that vibration and oscillation, they are just the same. They are just a synonym of each other, or relatively the same thing. All right. And they are allowed to vibrate or oscillate freely. You just give an initial displacement to the particle or the object, allowed it to vibrate and oscillate freely. So the system will oscillate at a set frequency, because when in any system the oscillation occurs, इस system में oscillations occur होती हैं, vibrations होती हैं. So you always have a time period, and when you have a time period for those oscillations, so you do have a frequency then as well. Frequency भी होती है, it's given by f equals to 1/2. That is how many oscillations are being produced or are occurring in a system in 1 second. That is what frequency is. ठीक है ना? So the system will oscillate at a set frequency called the natural frequency. अब आप अगर उसको कुछ initial displacement देते हैं, ठीक है, जैसे कि पेंडुलम है, आपने उसको मीन पोजीशन से कुछ इनिशियल डिस्प्लेसमेंट दी, जस्ट पुश दैट और यू जस्ट हिट दैट स्लाइटली सच दैट कि आपकी फोर्स जो है वो नेग्लिजिबल है, एंड दैट एक्ट्स ओनली अ वेरी शॉर्ट पीरियड ऑफ टाइम. मैं अज्यूम ये कर रहा हूँ कि जो आपने इनिशियल डिस्प्लेसमेंट दी है, दैट इज ऑफ कोर्स बीइंग गिवन थ्रू सम फोर्स, बट दैट फोर्स इज very small, and that acts, and if it is not even very much small, so that acts for a very short period of time. ठीक है ना? So in that case, फिर आपका जो सिस्टम है, आपने इसको इनिशियल पुश दिया इस पार्टिकल को, and that force you have to make sure that acts not for a very short period of time, for just a fraction of a second. Just going to be, it should be a gentle push so that this particle gets some initial displacement, and then after it get displaced or oscillate freely. So whatever the frequency of those oscillations will be, that will be called as the natural frequency, F naught. We have seen from the last lesson that the time period for a pendulum only depends on the length and gravitational field. हमने देखा था T was equal to 2 pi square root of L or G over L. ये था. It was dependent on the gravitational field strength and the length of the pendulum. ठीक है. Whilst the time period of mass and spring only depends, और जो आपका spring mass system था उसमें आपका जो time period for the oscillation था जब आप spring को displace करते हैं was dependent on mass and the spring constant. ये हमने last lesson में learn किया था. These factors govern the natural frequency of a system. ये जाहिर सी बात है, अगर time period mass और spring constant पे dependent है या length और gravitational field strength पे dependent है, तो इसका अलावा की frequency जो natural frequency है वो भी आपकी जो है ना इन दोनों factors में in case of spring mass system और L और G and on L and G in case of pendulum पे फिर आपकी natural frequency depend करती है. Just like you have the time period dependent on these factors, on these quantities. ठीक है ना? And that is what we call and if an oscillating particle oscillates freely, that's what we call as free oscillation or free vibration. Or if an oscillating particle is oscillating at the natural frequency, so we then refer to those oscillations as free oscillations or free vibration. And this, on the contrary, we have the forced vibration or forced oscillation. That is when you have a driving force that is continuously making that oscillating particle oscillate. And when you have some driving force that is making any object or particle oscillate, so you're going to have you're not going to have, then that object or particle is not going to oscillate at natural frequency. It's going to oscillate at what we call as driving frequency. And all right, that will be oscillating at some frequency which we call in physics as driving frequency. Or in other words, if you yourself just make that pendulum get displaced or oscillate by your force, so of course then in that case whatever the frequency of the oscillation is not going to be the natural frequency, but that's what we call in physics as driving frequency. Okay, now what is resonance? So if I hold one end of a slinky spring, let the other oscillate freely. अगर मैं एक एंड से एक स्लिंकी स्प्रिंग है और उसको मैं होल्ड करके दूसरी तरफ उसको अलाउ करूं कि वो ऑसिलेट करे फ्रीली, जस्ट ठीक है ना, यहाँ से मैं होल्ड किया हुआ है और मैं उसको ऊपर नीचे डिस्प्लेस करूं ताकि जो उसका अदर एंड है दैट मे बी दैट इज अलाउड टू ऑसिलेट फ्रीली. सो वी हैव अ फ्री वाइब्रेशन सिस्टम. इफ आई मूव माय हैंड अप एंड डाउन, ठीक है ना, I force the slinky to vibrate. अगर मैं अपने hand को ऊपर नीचे move करूँगा, so I'm just making I'm just actually forcing the spring, forcing that system to oscillate at a certain frequency. But if I'm just holding it and allowing it to oscillate freely, then it's going to oscillate at natural frequency. ठीक है ना? And every system has its own natural frequency depending on certain factor. This just the way I have told कि आपके पास अगर spring mass system है, आपकी natural frequency will depend on mass and spring constant. Similarly, अगर आपका pendulum system है, तो आपकी जो frequency है, it's going to depend on the length of the pendulum, the gravitational field strength. तो अगर आप किसी system को allow करते हैं कि freely oscillate करे, it's going to oscillate at natural frequency, and it depends on the certain factors depending on the system. But again, you may make any system oscillate at a certain frequency other than the natural frequency. That's what we call as in physics as driving frequency. So, and I've just given an example that if I just if I just move my hand up and down and make this slinky spring oscillate at a certain frequency, that's the frequency of my hand is going to be what we call as driving frequency. This frequency में अपना hand move करूँगा, उसी frequency पे आपका system oscillate करेगा. That's what is called as driving frequency. And so when that frequency is lower than the natural frequency, the oscillations have a low amplitude. अगर आपकी जो ड्राइविंग फ्रीक्वेंसी है अगर वो नेचुरल फ्रीक्वेंसी से लो होगी तो फिर आपकी जो एम्पलीट्यूड होगी यानी जो मैक्सिमम डिस्प्लेसमेंट होगी वो कम होगी फॉर एवरी ऑसिलेशन, ठीक है. बट when the driving frequency is the same as the natural frequency, the amplitude increases massively. लेकिन if you yourself make any particle, अगर आप खुद एक particle या object को oscillate कराते हैं at a frequency equivalent to the natural frequency, then you would observe a drastic increase, a massive increase in the displacement, in the amplitude of the system. ठीक है ना. यानी कि जिस फ्रीक्वेंसी से जो आपकी जो ड्राइविंग फ्रीक्वेंसी है, जिस फ्रीक्वेंसी से आप सिस्टम को ऑसिलेट करा रहे हैं, if that gets equal to the natural frequency of the system, so you will observe a rapid or a drastic increase in the amplitude of the system, and that is what we call in physics as resonance. ठीक है ना. What you can see now, this is your driving frequency. So if you increase a driving frequency such that it gets, when you get closer, when the driving frequency gets closer to the natural frequency, so you can see that there's a very drastic increase in the amplitude. That's how the graphical representation is for the variation of the amplitude with the driving frequency. Okay, na? So you can see when your driving frequency is near your natural frequency, so you have a very large amplitude of the system. ठीक है ना. And this is what we call as an exponential increase. The exponential increase कहलाता है. ठीक है ना. The driving frequency is higher than the natural frequency, the amplitude of the oscillation decrease. अगर आपकी driving frequency again if it exceeds the natural frequency, तो फिर आपकी driving frequency फिर आपकी amplitude again decreases exponentially, and the more it exceeds the natural frequency, the lower the amplitude of the system will be. बात समझ आ गई तो?
जी सर.
Your